All right. Hello, everyone. Welcome to VSTG. Today we have a presentation by Dr. Martin Guitreau. He's talking about silicon isotopes and granitoids, a game changer for early Earth environments. Andre, can you please go ahead and introduce Martin for us?
Yeah, it's a pleasure to introduce Martin. Martin is assistant professor in University of Clermont, France, and he has quite a diverse experience, mostly focused on evolution of early crust and early history of our planet, but in general, like using uranium lead system and lutetium hafnium, as well as silicon isotopes to constrain sort of when crust evolved and when plate tectonics started. So he did his undergraduate also in Clermont, France, and he continued with a master and PhD in Lyon, where he started to work with Jean Blachard Toft and Hervé Martin on TTGs using lutetium hafnium system and also working on zircons. He then followed with a postdoctoral appointment at University of New Hampshire with Sam Mukasa, continuing work and expanding it to Harvard, Creighton, India, and Pikes Hill in US. He had a 2-year appointment in the University of Manchester with Matthias Wilbold, and when he had a 6-year postdoctoral fellow appointment at University Clermont, Auvergne, where he is working now as assistant professor. So again, he's using lutetium, hafnium, uranium, thorium, lead, oxygen, and silicon isotopes, and using in terms of instrumentation, laser ablation, multi-collect ICP-MS, as well as ICP-MS. So with this, I pass it to Martin. Take it over.
All right, thank you for the introduction. It's a great pleasure to be here to be able to present some of my work. So it will be a bit different from what I'm used to do, because most of my presentations so far have been focused on zircon. I'm not sure I will have time to talk about zircon, although what I tell you about silicon isotopes are being now converted into zircon analysis. But so let's begin. So I've tried to make this presentation as for the broad audience as possible. And we'll have time, I guess, to discuss at the very end. So I really wanted to emphasize the use of silicon isotopes that have brought to me, I think, a great deal of information regarding the study of Archean granitoids, and they reveal some important insights into what happened in terms of interactions between building crust and surface conditions. So as you will see, silicon isotopes are not the way to definitively discriminate geological settings, which is more or less the kind of twist that I've given to that presentation. But what you will see is that they provide some information that constrain some of these environment and that models have to take into account. So for the outline of the talk, I will just briefly give an introduction about present-day geodynamics and talk about the relationship, at least what would like to see between granites and plate tectonics. Then switch to what silicon isotopes can actually tell you about granite petrogenesis. So it's more or less a review of what's been done between the early 2000s and the present day. And then go into the details of these Archean granitoids and what information they provide about their source and geodynamic environments in which they likely formed. And then I will conclude. So these small images give you a sort of summary of my approach, which is looking at granitoids as a proxy of the global geodynamics, which can be quite dodgy, but we have to deal with this at some point. So modern geodynamics have been understood and constrained throughout the years by realizing that continents have drifted apart based on geological arguments such as the continuation of craton blocks, the mountain chains, or the deformation at continental scale between different parts. I usually take, Africa and South America because of the coast complementarity. The fossil records also help to realize that continents have drifted apart. Following this, more likely in the 50s, when magnetic campaigns have been done in the oceans to map the bottom of the ocean floor, and realizing that there was a symmetry between the ridge axis. The ridge axis represented a symmetry between the different parts of the ocean plates, so that the ocean were spreading, and continental drifting and ocean spreading have allowed people to realize that ocean spreading was actually related to the fact that continents have drifted apart. When you look at the distribution of earthquakes at the scale of the Earth, they're not randomly distributed, but they're distributed in specific areas that correspond to plate margins. Of course, I'm referring to lithospheric plates. When you focus on specific areas like Japan, and you look at the depth of earthquake generation, you realize that the farther you go towards the continent and the deeper the earthquake, which actually maps the Wataty-Benioff plain, which is a good argument to say that this ocean floor that is generated at ocean ridges is recycled back into the mantle at these convergent plate margins. And this altogether allowed the realization that there were some sort of cycles that were later referred on as Wilson cycles, where you open ocean basins by rifting continents apart. And then at some point, due to density reasons, the ocean plate sinks into the mantle throughout subduction, and it closes that ocean basin, ending up with collision, and then following erosion, and you get a stable continent. And so the driving force of that mechanism is really the fact that the mantle is convecting, and we know that because the Rayleigh number, which is a proxy for initiation or triggering of convection, is beyond the critical value, which is around 1,000. And I like that drawing from Holden, which actually shows that this Earth geodynamics, at least in the present day, this is why I've put modern geodynamics, is a complex machinery that generates lots of ocean floor and then recycle it back into the mantle. Now that we know about the plate tectonics, one question that we could ask is, when did that started? And I've put this compilation made by Pauling et al. 2020, where you can see that there are lots of answers that have been proposed. So almost right from the start in the Hadean down to almost, the beginning of the primary era. So it reminds me of the debates about crustal growth that you can see here, where you have the cumulative volume of continents over time, and you have no simple answer and no consensus. But I think that asking the question like this, when did plate tectonics start, is not really the right way to put the question. It should be put more like in what type of geodynamic environment, or what kind of geodynamics could have occurred in the early Earth. Because what we're trying to discuss here is what geodynamic regimes or what geodynamic environments were characterizing the early Earth, and what drove the differentiation of the Earth, since it has huge implications on how planets evolved and so on. And also, if you're interested in studying the emergence of life, this actually bears in the debate. So I've put here a figure that's in a paper in Press where we've tried to summarize most of the models that have been proposed. I know that in detail, they don't actually summarize all of the models, but some aspects of almost every model can fit in any of these 6 cartoons. So it goes all the way from steep subduction, like you would get in the present day, to some sort of disrupted subduction, which we call the dripduction, to some sort of flat subduction, like what currently happens underneath some of the Andes. Also subcretion, which is some sort of scales stacking. It's another way of seeing subduction. To more like stagnant lead scenarios where you have either delamination that induce melting and construction of the crust, or just reworking of the base of the crust to generate some magmas that will create the crust. So these are the more or less summary of the geodynamic regimes that may have occurred on the early Earth. There had been a proposal in several papers using different approaches that there may have been a global transition at 3 billion. So I've taken, for example, the Van Kranendonk 2011 paper, where you go from a sort of a stagnant lead scenario prior to 3 billion years to more global plate tectonic-like regime for the last 3 billion years. This global transition is probably not likely, since if you look at the crustal record, so here it's a figure from Laurent et al. 2014, you see in several different places that are actually presented here that you have some sort of pattern in the construction of the crust with granitic magmatism specific of TTGs. I will come back to this acronym later on. So you have granitoid, juvenile granitoid, let's say, for a certain time between 200 million years to 300 million years. And then you have some specific granitoids that mark the stabilization of these cratons. And depending on where you look, you have granitoids of the same sequence that actually formed at different times. So this transition is likely to be local rather than global. That doesn't change much what we're looking at, but it's essentially that we'll get answers at the local scale rather than at the global scale, which is actually what we're looking at. But how we do that, how we get back to the Archean to understand the geodynamic regime. And to me, here's the problem that was well illustrated by this figure from Gary 2013, is that I presented very briefly and very simply how we got to understand and characterize plate tectonics in the present day. And it involved a lot of geophysical data and geophysical observations, which is illustrated here, cannot be done in the past, obviously. So we have to rely on the rock record to be able to get observations and to try to constrain these geodynamic regimes. Unfortunately, plate tectonics at various stages will induce magmatism. So this is what is illustrated here in this figures from Jacob et al. 2021, where you have different conditions where you have like ocean-ocean subduction with like a volcanic arc, typical like the Isu-Bonin-Mariana arc, or you have active convergent margin, and so on. But in many stages, even after collision, where you could see here and here, you will have magmas generated. And these magmas will most of the time form granites. So I've put granites in plural because I wanted to differentiate granites from the term granite, which is here in this Stokesian diagram where you have quartz, alkali feldspar, plagioclase, and feldspatoids. So granite is actually a rock in itself, but when I say granites, it's in a broad sense, or you could use granitoids. You will see that as well in the literature. So these granitoids, I wanted to give a definition so that we're all on the same page. So these are, to me, are quartz-grained, magmatic, and silica-rich rocks. Of course, we can give other definitions, but that's, I think, the simplest and one of the most accurate for the discussion we can have today. So these rocks are magmatic, and they're the backbone of the continental crust, which is something you can determine because of the similarity between the composition of the bulk continental crust and the composition of granitoids. They're very similar, which means that most of the crust is made of granites. And here you have an example of granite from India, which is an Archean granite. And one thing that's important to note, though, is that granites rarely represent magmatic liquids. They're essentially products of granitic magma crystallization. Sometimes they correspond to actual liquids, but it's very rare. And you have a big diversity of granitoids in all of these fields. So I'm presume that you're all very familiar with the Stokesian diagram, but it's a good way to introduce granites. So what can we do with granites in such case? So since we're trying to use the rock record to reconstruct the geodynamic environments that were going on in the past, you have first to look at if granite can be a faithful tracer of geodynamic environments. And that's what people have tried to do for a long time. And it works relatively well for plate tectonics in modern day. So here's a compilation made by Jean-François Moyen after work made by Pitcher published in 1887. So depending on the environment in which this granitoid formed, they will have specific composition. Here you have like an intraplate rifting environment where you have typical anorogenic granitoids. And depending on the different environments, you can have granitoids with various chemical compositions and various mineralogies. So I won't go much into the details because this is not the essential point I'm trying to make here. So if you go back to Stokesian and use a classification that many of you may be familiar with, which is the I and S type, the A type was included later on. And then there's also sometimes the M type that you'll see. So using Stokesian diagram, you can see that these granitoids actually preserve the memory of magmatic evolution, other known as magmatic series, when you can have the entire spectrum of granitoid that will help you reconstruct the history of your magmatic evolution, you can actually see this type of evolution for most of the I types. The M type will spread along the right edge of the Stokesian diagram, whereas the A type will go at the bottom and then go up as the silica increase through differentiation. And the S type will more or less remain in this area. This is because S-type granites that come from the melting of sedimentary rocks most of the time correspond to eutectic compositions. So when the first liquids that will form when you start melting a rock that is made of feldspar and quartz and some ferromagnesian minerals. But the other series start from mafic, more or less mafic magmas, and will evolve towards felsic magmas, silica-rich magmas, in which you will get most of your granitoids. And they most end up in the actual granite field. But as I said, granite can take many different appearances based on their mineralogy. And the mineralogy is reflecting the chemistry and the chemistry is dependent upon the source, the conditions of melting, and also the crystallization processes that the magmas have undergone. The most accurate, to me, the most accurate classification for granitoids is the one proposed by Barbarin, 1999, which is a compilation and let's say, reorganization of priorly done classifications. I just wanted to emphasize that the classical I, S, and A classification does not encompass the entire variability that we can see, which is reflected in these acronyms that can be hard to remember, but once you get into granite business, it's fairly easy, and it makes a lot of sense. But I don't want to disturb you too much with all these acronyms. What you need to understand is that granites can have various compositions that will reflect the chemistry of their source, the melting conditions, and the crystallization pathways. And in a sense, it can all be combined in this sort of summary figure, where most of what you will get is a crustal contribution for some granitoids, and for other ones, you have meltal contributions. So these are the source I was talking about. And the mineralogy will also reflect the partial melting conditions. So this was also summarized in this nice cartoon made by Moyen et al. 2021, where you go from a mantle-dominated system, which is the case of this type of granitoids, to a crust-dominated system, which is what's going on with these guys. So if we make the parallel with plate tectonics, to the right, you will get the intraplate granitoids. To the left, you will get to the left, you will get the crust reworking products, essentially after a continental collision. And in the middle, you have what's attributed to subduction, so mixed sources from mantle and crustal. And so this is what is usually done in the present day using zircon as a whole rock substitute, because it's well, for various reasons, but because it's easier to measure, and also because hafnium and oxygen in zircon can be preserved more readily than at whole rock scale. And so most of the time you will get mantle compositions in terms of hafnium, and crustal composition. Also oxygen will be elevated, hafnium will be low, and oxygen will be mantle-like, around plus 5.3 per mil, something like that. And hafnium can vary a little bit depending on the source. But so this can be used as a proxy for mantle versus crust dominated system. But yeah, I just wanted to emphasize that granites are not direct evidence of tectonic settings, but we're discussing the sources. But once you know what type of source melted in which conditions, which is the type of information that granite can provide you, you can start speculating about the environment. Fortunately, so I said that the continental crust is essentially made of granitoids. So we can use granitoids to track the geodynamic regimes back in time, since, as shown in this map of surface age distribution, the continental crust is actually a patchwork of crustal domains of different ages that have recorded Earth evolution for the last 4 billion years. And if we take into account detrital-zircons that come from the Hadean, like the Jack-Hill zircons, or some that were found in South Africa and throughout the world nowadays, we can extrapolate this evolution up to 4.4 billion years, which is not what you can do with the ocean floor, since it's recycled due to plate tectonics, and the oldest age we get for the ocean floor is about 200 million years. So that's what we're trying to do here. Take granite as a proxy for geodynamic conditions. And I have to stop a little bit to talk about these Archean granitoids, because when you go back in time and study these Archean granitoids, they're a bit different from post-Archean granitoids. So this was Hervé Martin's life work. He's not the only one who has worked on this. Ken Condy was also one of the persons who worked a lot on this type of granitoids. And so I'm not giving a course on TTG petrogenesis, so I won't go into all the details, but I just wanted to highlight some important differences between Archean TTGs and modern day granites. So these TTGs, so that's an acronym for tonalite, trondhjemite, and granodiorite, which are granitoid types. So these TTGs are sodium rich, and they're essentially composed of plagioclase, which is oligoclase, so close to that albite end member. And when you look at these normative diagrams, you can see in green, so that's the post-Archean granitoids. And in red, these are the Archean granitoids, those so-called TTGs. And CA is for the calc-alkali trend. So this is what the type of evolution that these granitoids will show. So as I said, these Archean granitoids are sodium rich. And one of their distinctive feature is also this lower enrichment in heavy rare earth compared to modern day granitoids. In terms of light rare earth, so from lanthanum to samarium, it's essentially similar, but it's for the heavy ones from dysprosium to lutetium. They're still enriched compared to the primitive chondrite, but they're less enriched. So the patterns are more fractionated. And this is actually one of the specific, or let's say one of the main features that helped understand their petrogenesis. So again, I will not go in too many details about TTG petrogenesis, but I just wanted to show the conclusions of the study that used trace elements, essentially, although major elements were also involved. If you take tholeite, typical of what you will find in Archean terrains, and you melt it in the amphibolite garnet stability field, these tholeite will mate and produce magma that will closely resemble some sort of average for TTGs. So here you see partial melting with 10% up to 50%. So you reproduce this actual pattern, and this is thanks to garnet, a little bit of amphibole as well, but thanks to garnet, which is a lover of heavy rare earth. And it works as well for major elements. So that's why I'm not going into all of the arguments. And this has been shown also by experimental petrology, where people have melted basalts in the amphibolite stability field and obtained magmas of TTG composition. So the way it works is you extract a basalt from the mantle through partial melting. Then this basalt will be remelted to generate tonalitic magma with a residue composed of hornblende, garnet, CPX, ilmenite, and more or less plagioclase, depending on the depth of melting. And then those tonalitic magmas can undergo fractional crystallization to account for the diversity of TTG granitoids that we find throughout, accumulate, essentially composed of hornblende, ilmenite, and plagioclase. Of course, I'm not talking about accessory minerals, but this is the big picture for granite formation. So I think that's what people agree on in the present day, this sort of scenario for generation of TTGs. And now it becomes hotly debated in which geological setting you're allowed to bring this basalt to melt to generate these TTGs. And this actually is a very important question to answer, since it can help solve that problem, the geodynamic regime ongoing, that was ongoing back then. So if we summarize the difference between modern and Archean crust, it's essentially a matter of the type of source that melts rather than the geodynamic context, although they can be different. But put in a different way, if you look at this pressure over temperature diagram, if you consider geothermal gradients, in the present day, the geothermal gradients looks like that. And in the Archean, it can be proposed that the gradient was a little bit shallower, so that when the basalts will reach a certain pressure, the temperature will be high enough so that the basalt can melt to generate TTGs. So this would occur in this field, which is yellow, and all the green lines, green curves, or the dehydration reaction curves, where you have actinic chloride, talc, zoisite, tremolite. So all the minerals that will provide water and will promote melting will actually be present. Rather than in the present day, you will basically reach the solidus, which is in red here, where you would actually melt, but the slab would be essentially anhydrous, so it couldn't melt. So in a nutshell, the difference between the modern and the Archean crust can be accounted for by plate tectonics, but with different way of working, with slight differences in terms of geothermal gradients. But it could also be formed in another context. And so that's when I think that silicon isotopes can provide some important insights. So I suppose that not all of you are familiar with silicon isotopes. So I will go through briefly through silicon isotope systematics. So silicon is mostly composed of 3 isotopes. One, which is 28 silicon, is 92% abundant. So its abundance is 92%, which means that the silicon you will measure is made of 28 silicon by 92%, and the rest a tiny abundance, 4.67 for the 29 isotope and 3.1 for the silicon 30. So for those of you who are familiar with mass spectrometry, there's a limitation right here because of the abundance difference, and which is one of the reasons why we cannot achieve the same precision as we achieve with oxygen isotopes, for instance, or other species when you have more evenly distributed abundances throughout the isotopes. Most of the data will show are shown in terms of delta notation, which is, I guess, something that many of you are familiar with. But this delta notation will be based on the 30 silicon. So it's the ratio of the 30 over the 28 in the measured sample, normalized by a standard. And we look at deviations on the per mil, which is classically what is done with the delta. Silicon isotopes in high temperature processes have not been done before, or not so much, I should say, before the year 2000s and the advent of MCI-CPMS measurements. But this is an old system. It was developed so that very early on. I like to show this these 2 papers, especially this one, where you see that back in '54, in the golden days of the isotope geochemistry, people started to measure silicon isotopes. Of course, it's very abundant. 75% in mass of the continental crust is made by silicon and oxygen. So it was abundant, relatively easy to measure. So it makes sense that this development occurred early on. Like many isotope systems, and I mean, I'm talking about stable isotopes, so there's no variations in abundances due to radioactive decay or radiogenic accumulation. And so, like many stable isotope systematics, they undergo fractionation. And of course, it's dependent on the temperature. So the lower the temperature, the higher the fractionation. And this is what we'll based on for the future studies. So for a long time, most of the work that was done with silicon isotopes was based either on meteoritic material or low temperature material, and also related to life, biogenic material. The reason is simple, is because of the analytical precision. And that's why people have started to focus on silicon isotopes in the early 2000s, because MCICPMS allowed better precision than priorly used techniques. As you can see so you have delta 29 over delta 30, you have huge variations in the pre-solar grains. So these are silicon carbide grains. You have lots of variations that are easy to characterize, even though you don't have a very good analytical precision. As you can see in plants, soils, river water, low temperature rocks or biologically derived material, you have a narrow range of variation, but it's big enough so that you can really well discriminate your measurements. So to give you an idea, analytical precisions that we can achieve nowadays using various techniques from SIMS to MCICPMS, they range from 0.05 per mil to 0.4 per mil. So that gives you the type of resolution that we have. And all the igneous stuff, more or less igneous, they're in this very narrow range where you have the composition of the bulk silicate earth. And it's hard to discriminate the rocks in this range. So that's why we needed a very good precision. So the Savage group published a series of papers on silicon isotopes in granitoids. And so this is from a compilation, but the original figure was published in 2010. When you look at volcanic rocks and a series also of plutonic rocks, where you see their silicon isotope composition versus their silica content. And what you can see is that you have a correlation, which was interpreted as a magmatic differentiation, or you will see the igneous array name in other publications. So it means that silicon isotope fractionate during fractional crystallization, and as magma differentiate, their silicon isotope composition gets enriched in 30 silicon, so in heavy silicon. So this is not surprising since, as I said, due to vibrational energy in the bonds between atoms, there will be fractionation depending on the type of mineral that you will form. And here you can see some ab initio calculations of isotopic ratios. So these are like theoretical isotopic ratios depending on the bond length and on the polyhedron volume. And apart from zircon that has a twisted crystal lattice, there's a good correspondence. And what you can see is that when you crystallize ferromagnesian minerals, they will have a lower isotopic composition compared to more felsic minerals. And since they are the first, more or less, the first minerals to reach solidus during magmatic differentiation, the fractional crystallization of ferromagnesian minerals will induce an increase in the silicon isotope composition of these magmas. So here's the igneous array I was talking about from another publication from Poitrasson and Zambardi. And there's a group of granites that plot below that igneous correlation. And these are leucogranites. And this is because during low temperature alteration or weathering of the granitoids at the surface, there will be clay formation. And that was shown by Ziegler 2005. So here's the bedrock with the granite, and here's its composition. So the whole rock is approximately at minus 0.2 per mil. And as you go up the saprolite and the formation of the soil, you can realize that kaolinite formation induces a shift in the soil composition, and you get to lower silicon isotope composition. So if you melt such material, you can explain why you have low isotopic composition. So it's more or less the opposite to what we see in oxygen isotopes. Oxygen isotope will have heavier isotopic compositions compared to a regular granite. This is what was shown also by Savage, where you, so it's the same graph more or less, but where you look at silicon isotope composition versus the aluminum silicon ratio. And if you form kaolinite, you get towards high aluminum silicon ratio, but low silicon isotope composition. And if you add some biogenic derived silica, you will get to high values. And this is what you see also in soils from different places where you get towards very, very low isotopic compositions. When you look at this compilation that was made by Savage, where he analyzed a lot of material as well, you can see that shales and detrital sediments also have very low isotopic compositions. So no surprise if you melt this, you get S-type granitoids that will record the low isotopic composition of their source. Now, if we get to Archean TTGs, so there were recent papers by Ley where he compiled previously published data. You find the igneous array here and here as well with the actual data in the background. And what you can see is that contrary to S-type granitoids, these Archean TTGs plot above the igneous array. And this is something that was priorly shown by Deng et al. 2019 and André et al. 2019. But to be able to make sense of these variations, we had to show that the mantle composition did not change over time, which is what we actually did in the Deng et al. Paper, where we analyzed komatiites and modern-day mantle-derived rocks. And as you can see with these histograms, they are very consistent with the bulk silicate earth composition. If you look at S-type, here's the distribution in blue. We mix the I and A-type because it's hard to discriminate them from each other. And it's this yellowish, orangish curve. And the TTGs that we've analyzed that came from various different places. So the TTG we measured are actually the ones I analyzed in my PhD thesis that came from most of the cratons and covered a time span from 2.5 billion years to 4 billion years. And in André et al., they analyzed only TTGs from the Cabal craton, but lots of them. And they consistently give this heavy value of around 0 per mil. So what silicon isotopes show you is that they can be used to discriminate granite types from each other, which is quite fantastic. But how can we explain the heavy signature in the TTGs? So it's fairly easy to explain for the S-type, but for the TTGs, how do we explain that? So if we look at this compilation from Kleiner et al. 2018, you have various types of rocks, so igneous metamorphic, sedimentary, hydrothermal, fluids. As you can see, most of the fluids have the tendency to have heavy silicon isotope compositions. And some of the sediments, including marine sediments and cherts, tend to have heavy silicon isotope compositions. So the question was, when you look at crustal sections in Archean terrains or in present-day oceanic lithosphere, you will have pillow basalts, and then you have mafic gabbros underneath. And in Archean terrains, you have some sedimentary cherts. And most of the cherts that are ocean derived will have heavy silicon isotope signatures. So what if, when you melt the mafic source of TTGs, you add a little bit of chert to be able to account for these heavy signatures. So this is what we modeled here. So if we start from a fresh basalt, which is here, if you melt it, depending on the residue and the pressure, you will get silicon isotope compositions that will be approximately around minus 0.2 per mil. If the melting occurs deeper, you can increase slightly the isotope composition. If you melt hydrothermally silicified basalts from that column that come from those fluids, hydrothermal fluids, you will have the tendency to decrease the composition of silicon isotopes. This is because the fluids will incorporate silica from the basalt, which is at minus 0.3 per mil. And once you precipitate silica, the fractionation between silica and the fluid will induce the fact that the silica will have a lower isotopic composition compared to the fluid. So it will go to the right. So in order to account for that heavy signature, you will have to have a fluid that is heavier than the bulk silicate earth. And this is precisely what you get from the chert. So if you mix a little bit of chert with this basaltic source, you can actually reproduce the field in which you will form the TTGs. So this arrow here will go towards the composition of cherts. It's zoomed in this area, but the cherts will have much higher composition, as you can see here. Can go up to plus 5 per mil. When you melt modern edekites, it can be accounted for by the depth of melting, as you can see here, but it cannot account for this heavy one. So you need to add a source, in the source, heavy, some material with heavy silicon isotope signature. So that was the Deng et al. Message. Now, if we look at the André et al. Message that were published in the same time, they looked at silicified basalts in the Kaaba craton. And there was another paper in 2022 where things can be seen a little nicer, I think. So if you look at the green stuff here, the green squares, they correspond to unsilicified basalts and komatiites. And if you silicify these basalts and komatiites, you will increase their isotopic composition, as you can see here. And when you analyze quartz veins in the silicified areas, you can actually see that they're heavy compared to the bulk silicate earth and compared to the unsilicified basalts. The same data can be, as on the left figure, can be found on the right figure. So now they're in black. It's called the Waza trend. And in yellow and red, you have those granitoids analyzed in the Kaaba craton. And as you can see, they fall on the 0 per mil composition that was characteristic of these TTGs. So here you have, instead of having a model like in the Deng et al. Paper where you search for a reservoir with a heavy composition that you can mix with the source, you clearly here have the petrological evidence for what actually melted to generate this TTG. So this silicification of this basalt is precisely what can be accounted for as the source for these TTGs. So you don't need to invoke any sandwich type stratification. You just need to have these mafic rocks silicified, you melt them, and you can generate the TTGs like that. Surprisingly enough, or not, the Most of the basalt you will find in Archean greenstone belts, as exemplified here as some pillow basalts in the western Dura Craton, show evidence of eruption underwater. And you have lots of cherts in these terrains. So silica and water were abundant in the Archean. And another interesting feature is that when you look closely at the stratigraphy, which is what was done by Abraham et al. 2011, and you look at how silicon isotopes evolved in this stratigraphy, which is complementary to what André did later on, you can see that when you have unsilicified basalt, like in here, you have silicon isotope compositions that are very close to the BSE, to the bulk silicate earth. And as you get to silicified domains with lots of chert, you will have an increase in the silicon isotope composition. And you can see that in many different places. So I just gave these two examples. And this silicification is really localized, so that you can see like here you don't have this shift towards heavy silicon isotopes, compared to here where you have this heavy signature. So there you go, you have that information. But in order to account for the signature, you need to have silica derived from oceans. And as I said, so most of the basalts were erupted underwater, and Archean greenstone belts show evidence for enrichment in silica because of that, those thick chert deposits. There are debates regarding the content of the dissolved silicon, which is presented here in micromole, in the ocean over time. But people agree on the fact that back in the Archean, there were lots of silica in the oceans, and they were saturated in silica, which I think is well illustrated by these two cartoons from Poitras 2019, when they show that the Archean ocean was saturated in silica, and you have chert deposition, a lot of silicification. And in the modern day, life actually scavenges the silicon in the ocean and keeps it at a very low level. And biological organisms like sponges are responsible for that. So that's a huge difference. So to summarize before the final conclusion, silicon isotopes are not telling you what type of settings, in which type of setting TTG formed, but it gives you a very, very important constraint to me, and that's why I titled this presentation A Game Changer for Early Earth Environments, is that whenever or whatever model you invoke for the formation of TTG, it has to account for the fact that these basalt have interacted with the surface before being melted to generate TTGs. So if I go back to these cartoons, you cannot really tell which one is the most likely, and silicon isotopes cannot definitively give the answer. But if you think about these stagnant lead models, like this one with delamination or melting at the bottom of this thick plateau, the only way these models are possible is if they form through accumulation of basaltic layers, and that you had enough time for oceans to deposit silica through silicification before piling up things. So these sort of stagnant lead models are not impossible to account for the formation of TTGs, but they have to take into account these simple facts. So you cannot just pile up lavas very rapidly, dry lavas, I mean, and then through underplating, you melt the lower crust, and then you produce these magmas, because they won't have this heavy silicon isotope signature. So they help refining this environment. That's the strength that they have in this situation. So here's the conclusion. So silicon isotope compositions vary between magmatic differentiation and between granite types, as I showed you. Low temperature weathering by aqueous solutions at the surface can modify the composition of, or can induce the formation of heterogeneous sediments, mostly what I call the clay effect, which will have low silicon isotope compositions. Ocean-derived silica will have high silicon isotope composition because the ocean itself has high silicon isotope composition. And if you melt this type of sources, you can actually, because this happens at high temperature, the fractionation would be very limited, and then you can preserve these isotopic differences, which is why you can see these differences in granitoids. So Archean TTG's silicon isotope composition reveal, and that I think that's what most important, that TTG interacted with the surface. And this is an important constraint to take into account in the models. And then another advantage of adding silica to mafic systems is that you slightly lower the melting temperature. It has more or less the same effect as if you add water. And so at lower temperatures, you can generate this type of magmas. So I'm sorry, I cannot provide a definitive answer regarding the Archean geodynamic regime or in which geological setting TTGs or Archean crust formed. But I think that using silicon isotopes in combination to other proxies like oxygen and hafnium will, in the future, we'll be able to refine our understanding of these geodynamic settings, provided that we try to integrate at the local scale field geology, petrology, geochemistry, and also maybe geophysics to sort of look at the architecture of the craton. And with this, I will leave you. Thank you.
Thanks, Martin. A lot of stuff. Cool. All right, we'll transition to question and discussion. We don't usually cut that at a certain point, so if you need to go, just let us know and we can cut it. Okay. People can raise their hand with the raise hand button at reaction. If you click reactions at the bottom of your screen, it's right there, or you can type it, and we'll ask it for you. So Greg raised his hand first, please. Greg Vitalik, go ahead.
Yeah, that was really interesting. I have maybe a bit of an ancillary interest, but you did talk about the decline of del 30 Si in soils, but you also showed a enrichment of germanium to silicon ratios on a molar basis. Yes, that one. The use of germanium to silicon ratios to distinguish paleosols from sediments fascinates me. But what really fascinates me is why. I have no understanding. Why are the silica ratios lower in soil, and why are the germanium to silicon ratios high? Is there any explanation?
Well, in this specific case, this is due to silica, because in quartz you have a very, very low germanium over silicon ratio.
Right, right.
And so if you add quartz or a silica-rich material, you will get this low germanium over silicon ratio.
The super low germanium ratios are universal for both aquatic and marine cherts, whereas soils have super high, like ratios up to 10 or 15, even in some cases. My question is why? I've been asked this and I can't explain it.
Well, I guess you would have to talk to Luc André, who's more specialized in this. I think I'm
Okay.
just getting into this question. Actually, this is really interesting because if you read this figure well, you don't necessarily have to use silicon isotope compositions, but you can only use germanium silicon ratio to actually show the same thing. What you can see is that quartz veins are actually quite low compared to other minerals. But for low temperature soils, I couldn't tell you exactly why. It's
something to do with abundance of water, presumably. An abundance of water might be related to alkalinity or something like that. You know, I'm struggling.
Yeah. But what you can see also is that in some waters you have a positive correlation between germanium and silicon. So they really behave the same way in many processes. And
Yes,
and I agree, for in certain instances you just completely mess up with that systematic.
and they're very close. Yes, it remains a mystery, but thanks so much. It was really interesting.
You're welcome. Thank you.
All right, Martin, I'd like to ask a question actually.
Yeah.
So you talked a little bit about towards the end silicon isotopes in aqueous environments. Do you know of any studies talking about silicon isotopes in authigenic clays or like glauconite? And with this recent discussion about reverse weathering getting kind of big, I'm sort of wondering if people have done some work on this. Glauconite, chamosites, granolites, these sorts of clay minerals.
I think there are. I'm not, very very familiar with this topic since I got into silicon isotopes a few years ago. So I'm catching up with all that history, especially as I focused on the TTG story. But looking at you must know Sophie Opfergelt's work and Luc André's work. They've worked a lot on alteration and formation of soils over time, and the interaction with water and ocean and so on. So yeah, I'm not so familiar with clay formation apart from kaolinite and smectite, but the other
Okay.
types I couldn't tell you. Sorry.
No worries, thanks. Just curious. All right, there's no hands up or things typed in the chat at the moment. We'll leave some time for people to speak up though. All right. Well, thanks, Martin. It was a
You're
good talk. So there's a couple more talks left before the end of the year or end of the season. Oh, okay. Paul would like to go ahead. Go ahead, Paul. You're still muted, Paul.
Okay, yeah.
So do I understand correctly that the complementary reservoir to the depleted seawater is chert?
Let me get back to that. To some extent, yeah, but the continental crust, I think, it plays also a huge role in the isotopic composition of the ocean. I think because when you will leach the rocks to form soils, and then you will leave behind some clays, this heavy silicon isotope composition, the water will get transferred to the ocean. So continental crust is probably more likely to be the complementary reservoir, and chert will be formed in between. I guess that would be my answer.
So is it possible then from the silicon isotope composition of ancient seawater to say something about the volume of continental crust?
That's a very, very good question. As far as I know, it's a little tricky because if you look at that record, I don't have the backup slide for that. But if you look at how it evolved, if we assume that all the data are correct, you see first an increase and then a decrease of the silicon isotope composition in the oceans. And it's hard to understand why, if you really look at crustal growth models, it doesn't really make sense because it doesn't complement the extraction of continental crust.
Well, of course, the trajectory of the continental of change of continental crustal volume over time is the unknown,
Yes.
maybe zero.
Yeah, it's hard to really understand that, since in most of the models there's one thing that's neglected, it simply because we have no actual way to accurately track this. It's the crust recycling into the mantle. If I go back to these models,
Yeah, I agree with that.
because if I go back really briefly to this part, so we essentially use hafnium and oxygen to compensate, or at least to use them as proxies for crustal extraction. But what we're really doing when we do that is saying either you rework crust or you add new crust to the crust, to the existing crust. But there's no way of determining what crust you remove from the crust and you put back into the mantle. And so that's why I think, yeah, the debates are still going on because of that uncertainty. And I agree with you that this is the big unknown in this.
As Richard Armstrong used to say, it doesn't make sense that a hotter Earth should have been less differentiated.
Yeah.
That's the curve on the top, and I'm with him.
Yeah, you assume lots of activity. Yeah, I agree.
Also, on the more general question about plate tectonics and its duration, plate tectonics is difficult to initiate, but easy to sustain. And it's difficult to initiate because if you have a stagnant lid for even a few tens of millions of years, the lithosphere becomes too thick and stiff to rupture. So you can't get plate tectonics started anymore. But the action of plate tectonics itself maintains areas of thin lithosphere perpetually. Thin lithosphere at spreading ridges and at magmatic arcs, which are sites where subduction can be initiated when a plate tectonic regime is ongoing. So my inclination is to think that some kind of plate tectonics, in other words, gravitational sinking of cold surface lithosphere into the mantle, started very, very early and has been sustained on this planet ever since. And that's why plate tectonics is both rare in the universe, but long-lived once it gets started.
Yeah, I think that, well, there are some models, essentially theoretical or numerical models, that would say that it's possible to initiate some drifting and maybe initiate plate tectonics in thick lithosphere. You just need to have not extracted all the heat-producing radioactive elements. Because if you add that thick layer, you actually block the extraction of heat, and then heat can accumulate, and then that's when you will have the focusing on mantle plumes that can actually produce some drifting of the lithosphere at the base and induce possibly drifting, and that can probably break apart a continent.
I'm skeptical of this because I think the radioactive elements tend to concentrate in the upper crust.
Yeah. I mean, once you start melting, these are mostly incompatible elements, and they would be removed. But if you have sufficiently accumulated them in certain areas in the mantle through metasomatism, maybe you can generate this kind of things. I mean, there are, as I said, theoretical models or explanation for some of the focusing on big plumes, like some of the traps.
Well, you know, the Indian sector of the India-Australia plate has the has the highest in-plane stresses, compressive stresses in the world. And the continental margin of India is loaded by 20 kilometers of sediment in the Bengal fan, and yet there is no evidence of subduction initiation at that margin.
Mm-hmm.
And that's because it's, 115 million years old.
All right, maybe I can swing this around and we can hear from Nadia. Nadia sent a question in the chat. Which TTGs from the Catfall Craton did you analyze? What age range did you look at?
So yeah, try to remember. So we analyzed all of the TTGs from 3.45, the Stolzburg, down to the younger ones at 3.2. I think we had Tisprit, Nelsorter, and so that's the ones we've analyzed in the Deng paper. But Luc André analyzed, I think, most of them. I don't have the complete list, but yeah, it's available in the paper. But it makes almost no difference since they all show the same isotopic compositions. And that was our surprise, because when you look at the chemistry of these TTGs, some will have the tendency to show slight plagioclase accumulation, a little bit of more differentiation, so that the silica content ranges from more or less 60-ish, 65, 64 weight percent up to 75. And no matter what type of compositions you were looking at, they all showed the same silicon isotope composition within error bar, which means that it's not a differentiation issue, but it's more likely to be, a source issue. But when you look into the details, in detail at silicon isotopes, but also oxygen isotopes, you may see some slight differences in the ages that may tell something about variations in the silicification, or maybe of the source itself. But yeah, this would have to be investigated further, I think.
Okay.
All right. Thanks, Nadia. I'm gonna take off. I have to get to a meeting soon, but if there's more questions, Andre can help out. So see you all later.
See ya.
Yeah, just a quick question, Martin. Maybe it's not your field necessarily. How large is fractionation between chert and seawater, and between clay minerals and I guess groundwaters or meteoric waters? Is it known?
Oh, so if I understand correctly, you're asking how much fractionation there will be between the actual fluid and the mineral?
Yeah.
So obviously it will be temperature dependent, but at the temperature we're looking at, we're expecting fractionations between, for instance, if you have cherts precipitating from high temperature hydrothermal fluids, you expect fractionation of about 0.3 per mil, something like this.
But like from seawater.
Yeah.
Coming from just seawater, sort of 20 degrees or whatever, 15
So at
degrees.
20 degrees, you would expect, I would say something on the order of 1.2, 1.5 per mil.
Okay.
So it's essentially looking at, silica precipitation from a fluid, from an aqueous fluid. And I think, that's on the order of, maybe 2 per mil. I don't have all the numbers in mind, but
and for clay minerals, is it about the same range? And
so for clay minerals, it very depends on the mineral. For kaolinite, you can actually, fractionate quite substantially. For smectite, it's not as strong. Let me see if I don't have that. Maybe I have a backup slide talk about this. I remember I've seen this one's. No, I didn't put it in here. So, yeah, I would need to look at this, but I think, yeah, that would be for smectite, that would be on the order of 4.5 per mil. And for kaolinite, it would be, yeah, more like 0.8, 0.9 per mil.
And it's in a positive direction towards high values, right?
No, low values.
Oh, towards low value.
Yeah,
Okay,
yeah.
so
Let me
it's
get
opposite.
back to this. Yeah. So between kaolinite and pore water, yeah, you have, yeah, more or less, yeah, 1 per mil, or maybe slightly higher than that.
Mhm.
But smectite would be, yeah, lower. Well, actually, you can see that here more or less. So that's a smectite trend, and this is the kaolinite trend. So of course, it's how you will modify the rock by replacing minerals with clay. So it doesn't totally answer your question, but kaolinite will definitely help reach lower values than smectite.
Okay, thanks, Martin.
But I know there are data in literature where you actually have the fractionation factors.
Okay, and before we leave for summer, we have 2 more talks. We will confirm them, but next week we have a talk by Tarduna on, I guess, early Paleomag. And the last talk will be about modeling deposition of snow iron formations during snowball Earth. So stay tuned, and after it we break until late September. So thanks, Martin, and see you all in a week.
Thank you.
Thanks. Bye.
Yeah, I heard Alec Brenner's thesis a week or so ago. It's excellent, so I recommend that talk.
Mhm. Which one, Alec?
Brenner
Okay.
on the Paleoarchean or Mesoarchean, whatever it is, Paleomag,
Okay.
Kupfall-Pilbara comparison.
And he is from which group? From
Harvard, I believe he's with Roger Foote.
Okay. Yeah, maybe we should
Is he
approach.
the person who's talking in VSPG?
No,
Or is that somebody else?
it's I think John Tarduna.
Okay, sorry, I thought
Yeah.
it was Brenner.
Okay, yeah, we should also invite Brennan. Okay.
He'd be a good person to get.
Mhm. So it's MIT. Okay. Yeah. Okay. Thanks, everyone.
All right. See you.
Good night. Bye. Thanks, Martin.
You're
Yep.
welcome.
But,
Bye.